Into chapter 8, which is about rotating objects. You saw that, when we talked about particles back in chapter 6, that we didn't allow them to rotate. Here we're going to allow rigid bodies to rotate as well as translate in this particular chapter. So we're going to be considering objects that are extended objects, but at least at first, and actually for most of the chapter, rotating about some sort of fixed rotation axis that isn't changing. So that's like this disk rotating around a fixed axis. And one thing to keep in mind is that different parts of the disk are actually rotating at different speeds. If you're on the outside of the disk, if this thing's going around at 3 RPM, well, let's say 300 RPM or something like that, a certain rotation rate, in the time it takes for one revolution, this thing has to go all the way around that large circumference there, whereas a point close to the center, in the time it takes for one revolution, only has to go this short circumference there. So different parts of the object will actually be moving at different speeds. Good to keep in mind. Now we're going to start using that third measure of angles because it's just going to make our formulas a little bit easier in this chapter. So we've already measured angular displacements, or how far something rotates or how big of an angle is, in two ways. Degrees, which most people are familiar with, and revolutions, which is another measure of angle. One complete 360 degrees is the same as one revolution. So you can think of a revolution as an angle measure. 90 degrees is a quarter of a revolution, or 0.25 revolution. So we can measure any angle that way. The definition of radians is, well, we compare or take a ratio of the arc length that we move along for a given angle theta divided by the radius. So it's a ratio of this arc length to this radius. Now, for different angles, the radius is going to stay the same, but the arc length may get bigger or smaller. So the arc length is really what's telling us about the angle. So theta in radians is just the ratio of the arc length to the radius of the circle that it's on. So for example, 1 radian is when s equals r, when the numerator and denominator are the same. 2 radians is when s is twice as big as r, so that would be somewhere over at about an angle to here, right? That angle in that location. How many radians are there in one revolution? Well, we can use this same definition and say, well, in one complete revolution, you've gone 2 pi r, that's what s would be, and you divide that by r and you get 2 pi. So there are 2 pi radians. 2 pi radians is the same angle measure as 360 degrees, which is the same as one revolution. In 180 degrees, of course, it's half of that. In 90 degrees, it's half of that. So pi over 2 is 90 degrees. And sometimes it's convenient to think of pi is close to 3. It's 3.14159. So pi is close to 3. Pi over 2 is close to 1.5. 2 pi is close to 6. That just helps you remember some numbers sometimes. Now, here's a more difficult problem, or at least superficially more difficult. If a bike wheel rotates through 42 degrees, how many radians has it rotated through? What's the equivalent radian measure? And as always, when we're changing units with which we're measuring something, we can just use a change of unit kind of thing by multiplying by 1. So this thing in here in parentheses, I'm taking my 42 degrees and multiplying by 1. And when I say 1, I mean the numerator and denominator are exactly the same physical thing. We just found out that pi radians is the same as 180 degrees. So there's no difference between the numerator and denominator, but I've written them this way so the degrees will cancel out and I'll be left over with radians. So to change something from degrees to radians, you multiply by pi over 180. So that's 0.733 radians. Let's get to some of our kinematics quantities that are analogous to position, velocity, and acceleration. So we're going to think of theta as a kind of angular position. If we have an object that can pivot around a fixed axis, theta will tell us what position it's in, angularly speaking. And so, operating by analogy, just like we said, the average x velocity is delta x over delta t. We're going to say the average angular velocity, and that's given the symbol Greek lowercase omega. I know it looks like a W, but you say omega when you see this sort of curly W kind of thing. It's the last letter of the Greek alphabet. Is the change in angular position divided by the change in time. So that's for average over, when it's rotated through a finite angle. And of course, nobody's really interested in the average angular velocity much. What we're really interested in is with what angular velocity is it rotating right now? And that's the instantaneous angular velocity. And what we do is just calculate the average angular velocity over a very small time interval that includes the time that we're interested in knowing the angular velocity. So omega is angular velocity. And, in words, intuitively, omega tells us how fast something is rotating, and the sign tells us in which direction the object is spinning, so about its fixed axis. So positive omega means theta is increasing with time. So we have to define which is the direction of positive theta. That's not always obvious, but we'll always be clear about that when we're using this in problems. Theta is increasing with time. Negative omega means theta is decreasing with time. Similarly, angular acceleration. Again, when we were talking about motion in one dimension, we said ax was delta vx over delta t. Similarly, we're going to say the average angular acceleration, which is given the Greek letter alpha, is equal to the change in angular velocity divided by the change in time. And nobody's interested in the average, so we're going to do the instantaneous is just the average taken over a very small time interval that includes the time that you want or that you're interested in. Again, in common language, alpha tells the rate and in which direction omega is changing. So alpha is 0 means you have a constant omega. It's spinning at a constant rate. If alpha is positive, well, as with regular acceleration with ax, it's somewhat less intuitive. If you have a positive alpha, that means if omega is positive, then it's speeding up. It's becoming more and more positive. Whereas if you have a negative omega, it's actually slowing down in that direction. And one way to think of that is the same way I suggested thinking about linear acceleration. In both of those cases, you're doing your best to trend towards a positive omega. If you already have a positive omega and you have a positive alpha, you're trying to trend towards a more and more positive omega. That means you're speeding up. Whereas if you have a negative omega, you got to slow down in order to get towards a positive omega. So, and then similarly for a negative alpha, that means you're trending towards a more and more negative omega, whatever you have to do for the direction you're spinning. All right, let's take a quick break.